Okay, this week we're going to talk about two-way mixed ANOVA. Sometimes it's referred to as mixed factors ANOVA. All right, so let's start with just what is a two-way ANOVA. So let's just forget mixed for a second. What do we mean by a two-way ANOVA? This is when we compare the mean differences between groups that have been split on two independent variables. All right, so for example, looking at maybe math achievement scores across race and gender. The goal is often to understand if there's an interaction between the two independent variables on the dependent variable. So in this example with math achievement and gender and race, we would want to know if there's an interaction between gender and race on the dependent variable math achievement. All right, and in EDRM 705, you learned about a two-way ANOVA with two between subject factors. For example, examining math achievement across gender and race. Another example would be exploring motor skills across gender and degree of visual impairment. All right, so what do we mean when we say a two-way mixed ANOVA or a mixed factors ANOVA? All right, now we've got one between subjects factor, so in our last example, gender or race ethnicity, and one within subjects factor. So for example, pre-post intervention, or say 3 different lighting conditions. The primary purpose is to understand if there's an interaction between the between subjects and within subjects factors. It shows whether the effect of one of the factors is dependent on the value of the other factor. All right, for example, you want to understand if preschool motor skills change over time, so let's say pre-post intervention, differently for boys and girls. The two-way mixed ANOVA would tell you if the intervention is more beneficial for one gender over another. All right, assumptions. Can we run a two-way mixed ANOVA? All right, what do we need? We need one continuous dependent variable. So our examples are math scores, motor skills, science efficacy. We need one between subjects factor that's categorical, and by this I mean nominal or ordinal, with at least 2 categories. So examples would be gender, race ethnicity, maybe student happiness on a 3-point Likert scale. Categories of a between subjects factor are unrelated, all right? So they are independent. So the genders or different races are independent of one another, all right? This means that the participants can only be in one group, and the participants in one group cannot influence participants in another group on the dependent variable. All right, we also need one within subjects factor that is categorical, and again, nominal or ordinal, with at least 2 categories. All right, if we have an ordinal within subjects factor, this is typically time. So it can reflect 2 or more time points, pre-post intervention, year 1, year 2, year 3. If we think about a nominal within subjects factor, this often reflects 2 or more conditions where the dependent variable is measured. So our kind of working example of multiple lighting conditions. Categories of a within subjects factor are related. They're measured on the same dependent variable at the same time points, or measured on the same dependent variable while undergoing the same conditions. So each participant is measured at each time point, or each participant undergoes each same lighting condition. All right, let's keep on with our assumptions. So the more complicated the test gets, typically the more assumptions we have. We also we need no significant outliers, which we'll assess with a box plot. The dependent variable is normally distributed for each cell of the design, and we'll look at Shapiro-Wilk there. We've got homogeneity of variances, so the variance of the dependent variable is equal between the groups of the between subjects factor. We've got homogeneity of covariances, and for this one, we actually will not check this assumption. It is not available in JASP. If you were to use SPSS, then you would use something called the box test. And then, of course, we need sphericity, which is the variance of the differences between groups should be equal. All right, so what is the purpose of a two-way mixed ANOVA? The general purpose is to establish if there is an interaction between the between subjects factor and within subjects factor on a dependent variable. Depending on whether the interaction is statistically significant or not will determine how and which results you report. The interaction is often referred to as a two-way interaction or two-way interaction effect. And significance implies the effect of one factor on the dependent variable to be dependent on the value of the other factor. All right, and an example here would be if we found a significant interaction between time of our motor skill intervention, so pre and post intervention, with gender. So maybe in this situation, maybe the intervention was more beneficial for one gender. All right, what about a study design? All right, so when are we going to use a two-way mixed ANOVA? All right, one possibility is your within subjects factor is time, and your between subjects factor consists of conditions that not everyone experiences. So an example would be examining motor skills pre-post intervention across an intervention and control groups. Another study design example would be your within subjects factor is time, and your between subjects factor is a characteristic of your sample, like a demographic. So an example would be examining motor skills pre-post intervention across gender where everyone experienced the intervention. All right, and then lastly, the third example here is your within subjects factor consists of conditions that everyone experiences, and your between subjects factor is a characteristic of your sample. So an example here would be maybe you're measuring fatigue after 3 types of exercise, low, medium, and high intensity across gender, a characteristic of your sample. All right, so let's talk about the Omnibus hypothesis test. There's going to be 3 Omnibus hypothesis tests, and those 3 null hypotheses would be: one is there's no significant within subject effect. So keep in mind with the two-way mixed ANOVA, we've got a within subjects factor and we've got a between subjects factor. So the first one is going to be the main effect for within subjects factor. So there is no significant within subjects effect or no significant difference between the means of the differences between all the times or conditions. All right, and again, this is referred to as a main effect of time or condition. And the test is irrespective of which group, meaning the between subjects factor the data is in. So this is just a main effect of time or condition. All right, and so again, this omnibus test you see here, we've got 3 times or conditions, and irrespective of the group, this omnibus test is going to tell us if at least one of these asterisks is different. So if the average between one of these time or condition comparisons is different. All right. The second null hypothesis is there's no significant difference between, or there's no significant between subject effect. Or said another way, there's no significant difference between the means of the groups. All right, this is referred to as a main effect of group. And again, here, opposite, the test is irrespective of which time or condition, the within subjects factor, that the data is in. So what does this look like? All right, so this is just comparing averages on the 2 groups here, group 1 and group 2, and the omnibus test is just here would just be saying that this particular mean comparison is different. So if we have, let's just say, 3 or 4 groups, the Omnibus test will tell you if at least one of the comparisons is different. All right, and then lastly, the last hypothesis test is about the interaction. So the null would be there's no significant interaction effect or no significant group differences across time or conditions. This is referred to as simple main effects, and it's basically pairwise comparisons. All right, and so within time one, so the Omnibus test set takes the comparison of within time 1 across the groups, within time 2 across the groups, within time 3 across the groups, and a significant interaction effect says at least one of those is different. All right, so let's go through a JASP example. So after implementing a social emotional intervention with preschool teachers, we wish to examine if preschoolers' gender affects if preschool's gender affects how social skills change over time, post intervention, and beginning of the next school year. So with the preschoolers data file attached with this lecture, step 1 is going to be to run descriptive statistics to check for normality and outliers. So notice the difference here. We're going to put our 3 social skill time point measures in our variables, but we're adding sex under split. So we're going to look at these measures across sex. All right, so notice here we get our output. So we get a 0 and a 1 for each time point. And in this data set, 0 is boys and 1 is girls. All right. And for looking at normality, we want to look at the p-value of the Shapiro-Wilks test. And we see that all 6 of these p-values are greater than 0.05. And so this is telling us that we can assume normality. All right. What about outliers? So we're going to look at our box plots. And we get a boys and a girls box plot for each of the time points. And notice at the post-intervention for boys, we've got 2 outliers. And also at the beginning of year 2, for boys, we've got 2 outliers. And going forward, we're just going to leave these 2 outliers in our data set. They are relatively they're not terribly far away, and we don't have a huge data set here, so we're actually going to just leave them in this example. All right, so we want to run our repeated measures ANOVA. So when you go to repeated measures ANOVA in JASP, again, you're going to start with your repeated measures factors. We're going to rename them from the default. We're going to make one pre-intervention, post-intervention, and year 2. And then we're going to add our 3 social skills time points to our repeated measures cells. And then for our between subjects factors, we are going to add sex in that box. And much like with repeated measures ANOVA before, we're going to check descriptive statistics, we're going to check estimates of effect size and omega squared. And then under sphericity tests, we're going to check Greenhouse-Geiser and Hunfeld, and we're also going to check homogeneity tests. All right, under descriptive plots, we're going to add our repeated measures factor for the horizontal axis, and we're going to add sex for the separate lines. All right, so let's start going through some of the output. So the first thing we need to do is check for sphericity. And we're going to go to our test of sphericity box. And again, as a reminder, we need Mauchly's W p-value to be greater than 0.05 to assume sphericity. And here we do not have that p-value greater than 0.05. So we cannot assume sphericity. So then the condition becomes, well, we've got 2 epsilons that we can interpret, Greenhouse-Geiser or Hunfeld. And the rule is that the Greenhouse-Geiser needs to be less than 0.75 or Huntfeld epsilon needs to be greater than 0.75. So we see here that our greenhouse Geiser epsilon is less than 0.75, so we're going to interpret this correction in our output. So the next thing we need to do is check for homogeneity of variances, and in our test for equality of variances, or the Levine test, we need all the p-values to be greater than 0.05, and we see here that at each time point all three p-values are greater than 0.05, so we can assume homogeneity of variances. Okay, after implementing, so at this point, we want to start thinking about our main effects. So the first one we're going to look at is the main effect for time. And again, we are interpreting the greenhouse Geiser correction. And so our main effect for time, the p-value is less than 0.001, which means at least one time point is different from the others. And we can see that omega squared, the effect size, is 0.026. So we have a small medium effect for time. All right, in this same output box, we can look at our interaction effect. The simple main effect for time times sex with the greenhouse Geiser correction is the p-value is 0.845, so that's greater than 0.05, which means there is no significant interaction between time and the child's sex. And then for our last main effect for sex of the child, the main effect for sex here, the p-value is 0.048, so that's less than 0.05, which means there is a significant difference in average social skills across sex, regardless of time. However, the effect size is 0.016, which is pretty small. All right, and then looking at our descriptives, again, 0 is boys and 1 is girls. We notice that at each time point, girls appear to have higher average social skills than boys, and there appears to be an increase in social skills for both boys and girls from pre to post intervention. But then we don't see much of a difference from post intervention to year 2. All right, so at this point, we want to look at post hoc comparisons since both main effects are significant. And so we're going to add time. So we're going to go back to JASP in our post hoc tests, and we're going to add time. We're going to check effect size and keep pool error term for repeated measures factors checked. We're going to check Bonferroni for our correction, and we want to flag significant comparisons. All right, why do we not need to run post hoc comparisons for sex in this data set? In this data set, we only have 0s and 1s, or boys and girls, and so there's no reason. Here the Omnibus test is only for that one single comparison, and so it's telling us that there's a significant difference between the boys and the girls. If we had 3 or more genders in this data set, or if we had included intersex in this data set, then we would want to run the post hoc test comparisons. All right, looking at the output for the post hoc comparisons on time, all right, we see that we've got significant p-values between pre and post and between pre and year 2. So regardless of sex, pre-intervention social skills are different. They're actually lower from the other 2 time points. All right, how do we report results in APA format? All right, this is probably just something you're going to want to keep up and use as a reference, both in the classwork, the homework, and on the quiz, as well as with the if you decide to run a mixed factors ANOVA for the project, then you'll certainly want to reference back to this. All right, so let's walk through what we did in APA format. There were 2 potential outliers at post-intervention in year 2 as assessed by box plot. We left these potential outliers in the data set. The data were normally distributed as assessed by Shapiro-Wilkes test of normality, and that those p-values were greater than 0.05. There was homogeneity of variances. Again, the p-values were greater than 0.05, as assessed by Levine's test of homogeneity of variances. Mauchly's test of sphericity indicated that the assumption of sphericity was violated. Mauchly's W with 2 degrees of freedom was equal to 0.606, and the p-value was less than 0.001. The Greenhouse-Geyser correction with an epsilon of 0.718 was used for the interpretation of results. There was no statistically significant interaction between time points and sex, and the F-test with both the interaction degrees of freedom, the residual degrees of freedom, was equal to 0.096 with a p-value of 0.845. However, there was a statistically significant main effect for time, and again, we report that F-test value with degrees of freedom for both the main effect of time with the residuals. And that F-test had a value of 88.245 and a p-value of less than 0.001, and an effect size of omega squared was equal to 0.026. There was also a statistically significant main effect for sex, and for that F-test, the sex degrees of freedom was 1 and the residuals was 91, and that F-test was equal to 4.007 with a p-value of 0.048, and the effect size omega squared was equal to 0.016. Girls had statistically higher social skills regardless of time, but the effect size was small. Post hoc testing using the Bonferroni correction revealed that social skills increased significantly during the intervention, but not once the intervention ended. And so here we report the pre-post mean difference of negative 0.4653 with the standard error of 0.401 and the p-value less than 0.001. And we report the mean difference also between pre-intervention and year 2 and the standard error and the significant p-value. And then we also report the mean difference between post-intervention and year 2 with the standard error and the p-value. All right, at this point, I think you're probably ready for the classwork example.